Next up, we have Sharon Glotzer from the University of Michigan.
Okay. Thank you very much. I want to start by also thanking the Welch Foundation and Kathy for inviting me to this fabulous conference. Unlike all of the speakers at this conference today and tomorrow, and all the gorgeous materials that they make, I make nothing. Well, we don't make materials, but we make models, and we make both computational models and theoretical models, and we develop software that allows us to solve these models and predict the kinds of structures that are possible through self-assembly of all kinds of different sorts of building blocks, and also to design and reverse engineer building blocks that will self-assemble into different kinds of structures. So we use computers to do assembly engineering towards this grand vision that we're hearing so much of today of matter on demand. Is this going to work? I'm just going to use this here. Boom. And so as a theorist, as a simulator, my interest is in understanding the assembly of materials building blocks to achieve this vision of matter on demand. I want to learn how different building blocks fit together and come together to create complex structures. I want to understand how the forces that are driving building block assembly conspire to produce structural complexity. And I want to discover the essential minimal ingredients that are needed to obtain desired levels of complexity. And we've seen gorgeous examples of all kinds of complexity here, many of which manifest in the hierarchical nature of the structure. And this is important to obtain multifunctionality by mixing and matching different materials together at different sorts of scales, and also for getting new kinds of properties. We saw this morning this beautiful talk by Chad on his colloidal crystal engineering using DNA, which is this very powerful platform for being able to dial in the self-assembly of all kinds of structures by combining DNA of different lengths with particles of different sorts of shapes and sizes. And as far as I know, this is still the most complex colloidal crystal structure that's been self-assembled with DNA in terms of the size of the unit cell. There's 123 gold nanoparticles in this structure. And in fact, different kinds of colloidal crystals are possible by manipulating the different kinds of DNA, I should say different sorts of clathrate colloidal crystal structures. We have another paper coming out soon where his group was able to make a colloidal quasicrystal using a different shape of nanoparticle, again with complementary DNA. This is a dodecagonal quasicrystal, and this is also has hierarchical complexity, like the colloidal clathrate crystal, and it's even more interesting because it doesn't have a periodic translational repeat unit. So it has but it's a very interesting kind of structure. And so these are some examples of some of the types of complexity that are possible, but I don't think we've ever even scratched the surface of how far we could go with self-assembling particles into complex structures. What's interesting is that there's many different kinds of nanoparticles and many different kinds of physical bonding elements that can be used to create complex colloidal crystal structures, and these are just a sampling of them. Some of the particles might be, instead of gold or silver, they might be semiconductor, cad telluride, cad selenide, cad sulfide. They might be rare earths. And the bonding elements, in addition to DNA, could be things like oleic acids, CTAC or CTAB, or other kinds of or small, short organic ligands, especially when the nanoparticles are very small, on the order of, say, just a few nanometers or tens of nanometers. And what these all have in common is that regardless of the size scale of the particles or the materials of the particles But the bonding elements, they can all self-assemble into structures that can be predicted and designed for. Now, while the field has progressed an incredible amount over the last 25 years in terms of what's possible today, I don't think it's obvious at all that nanoparticles should be able to self-assemble into any crystal structure it wants to, right? So if we think about all of the complex crystals that are possible from atoms and molecules, it is not obvious to me that we should be able to make any of them, not any of them, but all of them. Which ones can't we make with colloidal particles and physical bonding elements? Are there ones that are impossible to make? And if so, why? What's special about those? Because these particles, or I should say, despite these particles range in size over, say, 3 orders of magnitude in size, the point that, sorry, I skipped the slide here. The point is that as long as the system is ergodic, all objects, any objects can assemble into structures just in the way that atoms do. And by ergodic, I mean that as long as the system is able to, in principle, access all of the different thermodynamic microstates that are available to the system, then any objects can self-assemble like atoms. And that's because statistical thermodynamics doesn't care about the origin of the forces. It doesn't care what the physical bonding elements are. It doesn't care what the materials are. There's forces, there's different interactions, there's van der Waals interactions, Coulomb interactions, hydrogen bonding, but whatever they are, the origin of the forces is not important, and that's a very fundamental tenet of statistical thermodynamics, and it's something that I think is very profound because it means that we can really be ambitious when we start to think about colloidal crystal engineering. And because statistical thermodynamics doesn't care about the origin of forces, we can, from a point of view of theory and computer simulation, we can think about all of these types of particles basically as just patchy particles, particles with shape and that can be anisotropic, with anisotropic interactions made possible by how the particles are functionalized with their physical bonding elements. And by treating all of these different kinds of systems, from 1 nanometer particles to 3 micron-sized colloidal particles, as long as those particles are suspended in a solution and are able to rearrange and find their thermodynamic equilibrium structure, then we can describe all of them within the same conceptual framework. And so we do this with many experimental collaborators that constantly help us in validating our models and improving our models and making them more and more accurate. So now let me show you something that I think is surprising. Let me show you a molecular simulation. This is using a Monte Carlo simulation. So imagine that you have a bunch of these colloidal particles and they're in a beaker of water, and they're just undergoing Brownian motion because of the motion of the molecules that is constantly bombarding them, okay? That's what this simulation is going to show. And we start out with a bunch of particles. They happen to be truncated, tetrahedrally shaped particles, all identical particles. You can't see the particles now because they're all fuzzed out to indicate that we start them off in a disordered fluid state. And now I'll show you the simulation, and immediately we start to see that the particles start to self-assemble into these orange clusters. And then we start to see these red. What we do is we color the particles red as soon as they become part of the final crystal structure by the end of the movie. And so the original system starts out as a disordered fluid, then we get these clusters, and now all the clusters lock in place, and we end up with a colloidal crystal that's coexisting with a fluid. So this is a typical type of thing you might see in one of these experiments with particles self-assembling with physical bonding elements. But here's the thing. First, I should say that this crystal structure so far is the most, it's the largest unit cell we've been able to self-assemble so far in the lab. It has 432 particles in the unit cell, which is a very complicated unit cell. It's isostructural to something called the Bergman phase. It was discovered by Linus Pauling long time ago. But here's the thing, there are no explicit bonding elements. There's no DNA, there's no ligands. These are hard particles that have no attraction between them whatsoever. Their only rule is that they can't overlap. So they're billiard balls suspended in solution that go wherever they want to as long as they don't run into one another. That's it. So that means because there's no energy in the system, no potential energy in the system, the only thing in this system is entropy. So this system just went from a completely disordered initial condition to an ordered structure, a highly ordered structure, due solely to entropy. So some of you may say, what? That's not what I was taught in statistical thermodynamics class. So let me explain. So entropy, we know the fundamental tenet of statistical thermodynamics is that systems evolve to the most probable state. The most probable state is always the one that minimizes whatever is the appropriate free energy for your system. And if there's it's the equilibrium state, and if there's no potential energy, then the maximum, all you have left is T times the entropy. And so the most probable state will be the maximum entropy state if U is equal to 0. And then the Gibbs expression for the entropy simply becomes the Boltzmann expression for the entropy, which is that the entropy is equal to the Boltzmann constant times the log of the total number of microstates, meaning the total number of ways that all of the objects in your system can rearrange themselves. The more ways you can rearrange the objects, the particles, the higher the entropy of the system. And because there's no potential energy, all of the microstates in the system are equally likely. So this is actually like, the soft matter community knows this, but they've kept it a secret for a long time. Onsager basically told us that this would happen from the point of view of hard rods. And he thought about infinitely long, infinitely hard rods. But here's a simulation of shorter hard rods where it starts off disordered red, and then you see that the particles start to align. They undergo an isotropic nematic transition. And on the right, we have a prediction from Kirkwood that came earlier, actually, in 1939, that hard spheres would spontaneously order into a crystal once the density was high enough. It was demonstrated in one of the very first computer simulations done by Alder and Wainwright, who did molecular dynamics simulations, and Wood and Jacobson, who did Monte Carlo simulations around 1957, 1958. They took a year on whatever was the giant cray at that time. And the reason why these particles order is because there are more microstates available to the system, more ways of arranging the particles if the system orders than if it stays disordered. So if you think in terms of the spheres that happen to form a face-centered cubic crystal, there's a lot of wiggle room. You can move the particle, every particle that you move a little bit, it's still consistent with the macrostate of the crystal. If it stays disordered and you try to go denser, the system will jam. And so it's a very counterintuitive thing. Once the system is crowded, sufficiently crowded, hard particles can order. Okay, so if you don't believe that, you're in good company. It was argued over for 40 years until this definitive experiment that was run by Bill Russell and Paul Chaikin and the crew of the STS-73, or I should say the STS-73 space shuttle crew, that put PMMA colloids in toluene and flew it on the space shuttle because all of the experimentalists on Earth were doing it, density matching the particles in the solution, matching the indices of refraction to get rid of all the van der Waals interactions, and people still said, gravity though. So they spent millions of dollars to fly it on the space shuttle to get it out of gravity. And so that's the definitive proof of that. And then it took really 10 more years for us to realize just how powerful this idea of entropy-driven disorder-order transitions could be. And we've found this out quite by accident when my student at the time threw a bunch of hard tetrahedrally shaped particles into a box. And before we had a chance to turn on all the interactions that we expected to be in this system that we were working on with our collaborator, we looked at it and saw that these particles were ordering. Turns out that they ordered into a dodecagonal quasi-crystal whose nearest periodic proximate had 82 particles in the unit cell. So one of the most complex crystal structures formed by the simplest possible platonic solid. And again, this is due solely to entropy. And you could see this beautiful structure where they form on this, if you look on the side, they form these columns of pentagonal dipyramids separated by 12-member rings, et cetera, et cetera, et cetera. And it turns out that this quasi-crystal is isostructural to the tantalum tellurium quasi-crystalline chalcogenide. And we can match up the structure, the diffraction patterns quite well between the two systems. And I wanted to show this. I got this slide from Sing-Shen Ye at Indiana University. This was just published recently in JACS. He is the first to have made our particular quasi-crystal out of the same particles, of the same shape, by screening out all the interactions and drawing it really slowly in a droplet. And it's all of the same columns with the different kinds of packing. And I'll show this movie because I think it's just gorgeous that he did. It's a FIB SEM tomography movie that goes through the quasi-crystal, and you could see all of this gorgeous structure. So I urge you to go read that beautiful paper. Since that time, my students have run bazillions of simulations of all kinds of different shapes. This is a study that we published in 2012 where we studied 145 different shapes, 101 of them crystallized due to entropy maximization. And since then, we've now done maybe tens of thousands of different shapes. We have yet to find an atomic crystal structure that we cannot self-assemble in the computer with shape and entropy alone. So the new thing that we understand now that we didn't understand for 50, 60 years is that these emergent statistical, effectively attractive forces that are in the rod's case, aligning the rods, giving up translational degrees of, rotational degrees of freedom to gain translational degrees of freedom, or in the case of these tetrahedra, aligning their facets to gain more access to more microstates. These emergent statistical entropic forces are acting locally and they're acting directionally to produce valency that results in this great structural complexity, and an attractive local directional force between particles is something we might call a bond. So I call this an entropic bond. And we could quantify this entropic bond. One way to do this is using something called the potential of mean force and torque. What this basically shows is a probability map of if you're a particle in this case, an ordered diamond structure where 55% of the box is full of particles and the rest is empty. And you ask, I'm a particle here, what's my probability of having another particle here, or angled this way, or angled that way, and then project it down. And the blue spots are where you're most likely to see another particle. The red spots are where you're least likely. What's important about this is it allows us to put an energy value on this effective statistical force that's acting as though there's a local attraction between the particles, even though there isn't an attractive interaction between the particles. And it can be several kT. It can be much higher, depending on the sharpness of the facets of the particles, for example, or how dense the system is. And so what this means is that particles can be not only enthalpically patchy, but they can be entropically patchy as well. And that means we can trade physical bonding for entropic bonding and vice versa. This opens up the design space tremendously because it gives us this knob. And also, it's important to know, even if you're making materials where you have explicit interactions, like DNA bonding elements or anything in your system, it's helpful to know what entropy is doing. Because we're typically thinking that entropy is driving us towards disorder. But it's not always, right? And here are examples where entropy is actually might be synergistic with the order you're getting, or it might actually be trying to drive different order. And that means that you may not need as strong a bonding elements as you think you do, because entropy is actually helping to get you there. I think it's also really of fundamental importance. So here's an example of this, of a entropically self-assembled clathrate colloidal crystal. This is the same structure as I showed before that Chad's group was able to make in the lab with DNA. The DNA is pulling the particles together, and the complementary contact model is aligning those faces. Here, we are just confining the particles so they're close enough, and then entropy is doing the rest to bring the facets together. Now, it's not always so easy that we can use exactly the same shape in entropy. Sometimes we have to modify the shape a little bit. Now, notice here in this colloidal clathrate crystal, this is not really a host-guest clathrate like most clathrate crystals, like molecular clathrates, hydrate clathrates. It has a very small cavity in the cage size. So my former student, Sang-Min Lee, said, I wonder if I can take this, this particle shape, which happens to be, if you take two tetrahedra and you glue them together and then you squash them and you get a triangular, squished triangular bipyramid. He said, I wonder if I start snipping the corners, I can keep this crystal structure, but open up the cavity in the cage so that I can put guests inside. And this was on the cover of Nature Chemistry in July. Beautiful picture figure that he made. And in fact, yes, as you go from not truncated all the way, or very little truncated from the left and all the way more truncated to the right, you can get all these different kinds of colloidal clathrate crystals that are isostructural to the kinds of clathrates that water molecules can form with different kinds of guests inside. Some of these, so the largest unit cell we found this way is 340 particles in the unit cell, again, just ordered by entropy. Sometimes the small cages can actually be empty, while larger cages have particles in them. And you can even have multiple particles together in one cage, just like you can do with molecular clathrates. But now check this out. In every one of these clathrates, look at what the guests are doing. They're spinning like crazy. The host network is very rigid and moving together. So it's almost as though the entropy has compartmentalized. And the entropy is causing the host network to want to align in this way, but it's dumped all the rest of its entropy into these guest particles. And we can do this in the computer, if we go in and say the guests are not allowed to rotate, the structure just falls apart. If we take the guests out of the cages, the system, the network, spits out a particle into the cage to give it back the entropy that we took away by taking one of the particles out. So it's entropically stabilized, but in this, like all the other ones I'm showing, but in this very interesting way. Guess what else what else is stabilized in this way? Actual molecular cloth rates are also stabilized by rotation of the guest molecules inside, whether those guest molecules are methane or any NH2 molecule or different kinds of objects. They're rotating inside. This is just one of many, many papers that has looked at this stabilization of molecular cloth rates through the rotation of the guests. Another thing that's interesting is that molecular cloth rate crystals, when they form from a liquid, they don't just immediately crystallize out of like liquid water doesn't just crystallize into a cloth rate crystal. It undergoes liquid-liquid phase separation into two coexisting liquids, dense water and less dense water. And then at the interface between those two different liquids is where the cloth rate crystal grows. So we asked, well, is that possible in these colloidal crystal systems just with entropy alone? And if you remember back to your thermodynamics class, you may recall the van der Waals equation of state, which modifies the ideal gas equation to state in two fundamental ways. It says, you know, by the way, atoms have size, so we're going to subtract that off of the volume. And also, their atoms are attractive. So we have to put in this term, this attractive term, that goes like 1 over v squared. And van der Waals said that's the minimal you have to have if you want to have a phase transition from a gas to a liquid, right? If you want your atoms to cohere into a liquid. And that 1 over v squared term is essential because without it, you can't get this inflection point, and so you can't get the phase transition. You can't ever have two coexisting liquids, or gas and liquid, at one pressure and two different densities. So we don't have any explicit interaction, so we shouldn't see that, right? But of course we do. And so here's one of those cloth rate crystals that starts off disordered at the top, and then we took out the low density liquid. The dark blue is the high density, I shouldn't call liquid, fluid phase, right? There's no explicit attraction, so it's a fluid. And then the red cloth rate crystal grows at the interface between the dense fluid and the less dense fluid, just like in a molecular cloth rate crystal. So apparently, and here's another one that I like, which is a pentagonal bipyramid, that's the prolate pentagonal bipyramid, that also undergoes fluid-fluid phase separations into two coexisting fluids, one dense, one not so dense, and then this green crystal just starts growing. It acts for all intents and purposes like there are real local physical attractions between the particles, but there are not. And this thing makes a crystal with 244 particles in the unit cell. So apparently, effective attraction is sufficient to drive this kind of phase transition. So in the last couple, I have no idea what time it is. I'm just gonna go. Where's dude? 5 minutes, perfect. So, you know, the fact that the same complexity and diversity of both crystal structure and kinetics is possible with chemical bonds, where electrons are involved, with physical bonds, and with entropic bonds is really pretty remarkable, I think. And so the question that we're looking at now is, can we create a first principles theory of entropic bonding that's kind of parallel to the first principles theory of chemical bonding that computational chemists use all day long to find preferred crystal structures and other types of structures of atomic and molecular systems. We want this because we have simulation, we have statistical thermodynamics where we can, you know, just run computer simulations, whether it's molecular dynamics or Monte Carlo or whatever. But this would be an additional powerful tool that would allow us to potentially screen many, many different structures all at once in the way that we do now for atomic crystal structures with electronic structure theory. It would also allow us an apples-to-apples comparison between atomic and colloidal systems that are forming the exact same crystal structures, so we can understand the origin of the structural complexity, right? If you have the exact same crystal structure out of a bunch of Dungeons and Dragons dice that are floating around in a box, and also some atomic elements, right? We know that the forces are different, but what is it that they have in common that they would access the same kinds of structural solutions? And maybe this could actually provide us a deeper understanding of atomic systems using only shapes. So it's hard to do this, and here's why. Because for ab initio theories of chemical bonding in atomic crystals, you have your atomic crystal, but you have electrons. And in electronic structure theory, the thermodynamically preferred arrangement of M atoms with N interacting electrons is the one that minimizes the energy of the total electron density. So you have to solve for the optimum electron density, and that was really hard to do until Cahn Sham came along and said, instead of that, we will posit that the ground state electron density of an N electron system of M atoms, which we can't solve because the electrons are interacting, that will be identical to that of an auxiliary system of N non-interacting electrons, as long as those electrons are moving in some external field due to the nuclei that are fixed, and we have to figure out what that external potential is. And there's probably 100,000 papers published on finding that external field and what's called the free energy functional of the system. And that's how all modern day, forms the basis of all modern day electronic structure codes. Great, but we have no electrons. We have shapes. And it turns out if you just try to do an equivalent kind of density functional theory of that, which many people have been trying to do for decades, you don't get very far. So instead, we thought, why don't we, since the system has this parallel with atomic structures, let's treat the shapes as the nuclei, and then we'll make up some mathematically fictitious pseudoparticles that we'll throw in there as a kind of a measure of the local entropy density, and I say that very loosely. And I don't have time to go into all of the details, but basically what we're saying is that the thermodynamically preferred arrangement of our M hard shapes will be identical to that in an auxiliary system of these N fictitious, a fluid of these pseudoparticles moving in an external field that we then have to solve from that's arising from the fixed hard shapes. So we still have to find this field and show that this actually works in the same way that Cahn Sham did for atoms. And we've done that using a classical density functional theory approach. We found a functional. We found this external field. We can solve this. And if we minimize it, then we can set up different crystal structures. So take the same particle, same densities, try different crystal structures, minimize this functional, see which one has the lowest free energy. That's the one that wins. Same way you would do with atoms. And so as just for example, here's a bunch of crystals that form the crystal structure changes as you truncate the particles. And on the left is our entropic bonding theory calculation of the relative free energy of all of them. And the color bar at the bottom, as you go from your left to right, shows which crystal structures have the lowest free energy of the ones we tried as a function of truncation. So first it's the quasicrystal, and then it's diamond, and then it's another one, and then it's another one. And the black lines are what we found just by doing Monte Carlo simulations over a decade ago. And so the theory is picking up all of those transitions. Once we've solved this, we have now this just like in atoms you have the distribution of electrons, and they show you what the bonding states look like. We now have this entropy distribution, if you will, and so we can take that density distribution and we can expand it around the particles like you do for atoms, but not with spherical harmonics, but in shape harmonics. The spherical harmonics would make no sense around a cubic particle, so we use a cubic harmonics. And by doing that, we get these harmonics, which we can visualize as orbitals like we do for atoms, and then we can calculate the effective bonding strength in different kinds of configuration. And that's what's shown here for a couple of different particles. What we can do now is we can then take, say, carbon atoms in diamond, calculate the bonding states using electronic structure theory code, and then we can find the electron distribution. We can map it to this entropy distribution and reverse engineer what shape will give us that back. Then we get a shape that's supposed to self-assemble into diamond. So we try it by throwing it in a simulation and seeing what comes out. And so far, this seems to work. So we're working very hard to validate this and try it on all kinds of different systems. The vision, eventually, is to see if we can come up with a periodic table of shapes. Like perhaps every element, depending on what it's mixed with, what crystal it's in, can actually be represented by a family of shapes, a different shape in every situation. But maybe that family of shapes has something in common. And then we can learn something about why atoms form the crystals that they do and use that to design colloidal crystals. And so these are some of the takeaways. And of course, a next step would be to now bring interactions into the story. Because now we can do this just with entropy. Of course, we can now put in explicit interactions, which will change the entropy. But it should allow us to have this kind of powerful tool one day. So I will finish by putting that up and say thank you again for the invitation.
Thank you very much, Sharon. So we have time for questions. If we can raise your hands, I'm going to actually take advantage and ask the first one, if that's all right. Really amazing talk. You showed that we can use entropy to create many structures. I think you said tens of thousands now that you've done computational studies on. Can you give us a sense of what is kind of the major hurdle to experimentally validating some of these structures and actually going and making them? For example, is it the precision in shape, or should we be making these all in space?
So there's a couple of things I'll say. One is that when the particles are too small, it's almost impossible to really screen out all the interactions, like the van der Waals interactions. So the particles can't be too small. Then you have to be able to confine the particles. Let's just say that you could screen out all the interactions. You have to particles just have to be confined, right? If they're just free to go, they'll just expand like like air in the room. So you have to be able to confine them. And so not very recently, but recently, many of our collaborators are now starting to dry droplets in coffee rings, and they're able to control by changing the hydrophobicity and hydrophilicity. They should use your thing, Joanna. They should use yeah. So they control like the rate at which things order and what the surface is doing. And so now it's possible to do this. So the question is whether it's practical, right? So this is not a crystal now that you can take out and set it on the table, right? Because as soon as I take it out of confinement, it wants to fall apart because there's nothing actually sticking it together, right? So it's not necessarily practical to only use entropy, right? You could have much more control by using things like DNA. But I think that the reality is that entropy is playing a role in all of the systems that everybody's looking at. In some cases, it's just irrelevant compared to the enthalpy. In some cases, it's actually really important. And it might be competing with your enthalpy and keeping you from getting the crystal structure you want, or it might be synergistic, but then your effective interactions are so strong that it's like you quenched it and you just get a mishmash, right? So it's important to know what those contributions are. And then I think also just fundamentally, it's crazy that you should be able to get all these things with just entropic forces, and I think we need to understand that better.
Thank you. Other questions?
Did I understand you correctly? You
Where?
said
Where?
right over here.
Gotcha.
You created more microstates with order.
Yes.
So there's more disorder in order?
Yes, that's exactly right. Because the disorder is not the spatial disorder. It's what you don't know about the system. It means if you had to, at any moment, guess what microstate is it in, you'll have a harder time guessing when it's ordered. There's more microstates, right? So it's the disorder. It is absolutely disordered, but not in the way that we think colloquially and in a sense of spatial disorder. It's much better just think of entropy. Don't ever think about it as disorder. Think about it as just ways, about options, about lack of information. The less information you have, the more the entropy.
So do I have to go back and change my freshman chemistry lecture?
Probably. I could give you some slides.
Other questions? And name and affiliation. I failed at doing that myself. Bad example.
You did. Right here.
Craig Hawker, UC Santa Barbara. So I was really curious, and building on Zach's question, can you handle dispersity in both size
Yes.
as well as shape?
Yes.
And what is the impact of those?
So the impact is, this is super profound, it depends. So it depends on the structure and how forgiving that structure is to size or shape, polydispersity, or rounding of the edges, or like just broken edges or whatever. For example, for the dodecagonal quasicrystal of hard tetrahedra, and I always have to preface this by saying at what density, so like at, say, 55% packing fraction. We can have up to 12% size polydispersity, and it will still assemble the quasicrystal. It just won't look very pretty. You can round it a lot more than you think, and still get it, still get the quasicrystal. So that structure seems to be very forgiving, right? So as long as the facets are aligned. But of course, if you truncate it too much or they're too polydispersed, then hard spheres won't crystallize above 11% polydispersity. But once you have these facets, the entropic bonding between them is so much stronger than between spheres, right, that it's more forgiving in that sense. Then, of course, you could always add depletants in, which is also an entropic force, right, to increase even further the entropic bonding strength between different sides of your particles, if you will.
All right, I think with that, we'll go ahead and thank Sharon Glotzer once again.